right, Unit 1.5 is all about what are called nuclear reactions. And a nuclear reaction is a little bit different from what we refer to as typically as a chemical reaction, because a nuclear reaction involves the nucleus. And anytime you mess with the nucleus of an atom, you're messing with the stability of that atom. Okay, now, like we talked about with isotopes the day before, most elements do have more than one naturally occurring isotope, and these isotopes can be what's called radioactive. And when something is radioactive, all that means is that that element over time slowly breaks down. I think I mentioned carbon-14, which is something that all of us have in our bones. It also is radioactive, which means over time it breaks down. So a lot of times they use carbon-14 to figure out how much or how long ago something lived based on the amount of carbon-14 that is still left inside the bones that are found. So here in the Tri-Cities, for example, if you look this up, there's a discovery called the Kennewick Man, where they found some bones from somebody that they believe lived about 5,500 years ago. And they're basing that off of carbon-14 and the amount of carbon-14 still left in that person's body. Okay, so many times when you have these isotopes of different elements, they have a different number of neutrons, and that makes the nucleus become unstable. And again, when radioactivity happens, sometimes, not always, clearly as the carbon-14 in our bones disappears or decomposes, we don't release this. But many times when radioactivity happens, there is a release of high energy rays, which again happen because the nucleus of the atom is affected. Okay, so some of the ways that chemical reactions are different from nuclear reactions. Okay, chemical reactions happen when these bonds are broken. So basically in a chemical reaction, we're only talking about the electrons that are sharing, switching, getting lost by one atom, gained by another. They have very, very small energy changes. But again, the atoms are still the same atoms, but they might gain, lose, or share electrons to become more stable. Okay, with nuclear reactions, obviously we're talking about the nucleus. Okay, when nuclei, which is nucleuses, when multiple nucleuses combine or split, or one nucleus splits, it can give off a lot of radiation, a lot of energy. And we're going to talk about those types of radiation here in just a minute. Okay, there's very, very large energy changes. And many times with a nuclear reaction, because the nucleus is being affected, it actually will change elements. The number of protons will actually change and switch from one element to another. So really big differences there between chemical and nuclear reactions. So there's three different types of radiation that are given off when a nuclear reaction happens. One of them is called alpha radiation, one is called beta, and one is called gamma. Okay, and gamma really are the really, really bad ones. We'll talk about here in just a second about what that means. Okay, let's talk about alpha. Okay, an alpha particle, if you notice it, it's really nothing more than a helium atom. Okay, there's a little difference. It's a helium atom with no electrons. Okay, and the way that we write, well, how would you write normal helium? You'd write helium has a mass of 4, it has 2 protons, so you'd put the little 4 in the 2. But again, because it has no electrons, it still has the 2 protons, but no electrons. So it does have a charge of positive 2. Okay, now these particles are pretty large, and they move really slowly, and simply by having a piece of paper up, you could block that. Think about the helium in a balloon. I mean, the helium in a balloon stays inside that balloon because it's blocked by the outer layer of that balloon. Okay. So here's an example of this. If the element radium, element number 88 on the periodic table, decomposes by way of alpha radiation, it turns into the element radon, and it gives off that alpha particle there, which again is still nothing more than a helium atom without any electrons. Okay, So that's what we just talked about. Again, notice though that the masses, that 226 here, is still the same. 222 and 4. The 222 and the 4 still add up to 226. And then notice that the total mass of radium is 88, and that the total mass, notice that the 86 and the 2 still add up to 88. Okay, a beta particle, so the second type of radiation here. So alpha particle was first, which is just a helium atom without any electrons in it. Okay, a beta particle is not a nucleus at all. It's not an atom. It's just a very fast-moving electron that is emitted. And when that happens, when beta radiation happens, one of the neutrons converts into a proton. So that neutron becomes a positively charged particle rather than a negatively charged particle. Okay, so many times you'll see a beta particle written, which is that letter B with a little tail on the end of it. Or, since it's just, again, a fast-moving electron, a lot of times you just write a beta particle as just E minus. Okay, because again, it's nothing more than an electron with that -1 charge. Okay, so beta radiation is a stream of lightweight, fast-moving electrons. It does require a little bit more than paper to block, so an alpha particle can get blocked by a piece of paper. It does require some metal, usually a piece of metal foil will stop. So now you're thinking about the people in like the suits when they go into radioactive areas, you know, they're not wearing paper, okay, because it's not usually just alpha particles. It's not just a piece of metal. They're wearing some pretty extensive suits to help protect them, because we've got the next one coming up here as well. Okay, so here's an example of a beta particle being emitted from a radioactive iodine. So iodine, this is iodine with a mass of 131. Notice that again, it gives off that electron, and you're like, well, wait a minute, how did it change elements? Because remember that when a beta particle is released, a neutron is converted into a proton. So notice that in this case, that 53 now just became 54. Okay, so by adding a proton, you change the element, and one more proton added to iodine makes it xenon. Okay, so the element does change like it did with alpha radiation, again, because that neutron turned into a proton. Okay, but notice again that the mass didn't change. The overall mass didn't change there. Okay, and then the last one, these are the really, really bad ones here, okay? In the 1980s, I believe it was 1984, when one of the nuclear reactors in the Ukraine in Chernobyl basically malfunctioned and melted down, it released a huge amount of radiation. And the large majority of that radiation was caused by gamma rays, okay? And they sent firefighters in to try to stop this, and all of the firefighters died, all of their skin peeled off. The clothing that the firefighters were wearing are still in the basement at the hospital where they took them all, and to this day they are still giving off radiation in, 35, 40 years later. Okay? So gamma rays are really, really bad. Okay? Gamma rays are what are called photons. And again, we'll talk about that here in a couple days. And they're made up of high energy electromagnetic radiation. They do travel at the speed of light because, again, it's just energy. The other two particles are actually matter. Okay, alpha particles, beta particles. Alpha particles are helium atoms with no electrons. Beta particles are nothing more than electrons. This isn't either of those two. This isn't matter. This is energy. And this is energy that, again, very, very dangerous. They don't have a mass because, again, it's just energy. They don't have a charge. Again, energy, not matter. The emission of gamma rays, again, because it's energy, doesn't change the atomic number or the mass. But most of the time when gamma radiation is produced, you're going to probably see some type of alpha or beta radiation that also occurs. Okay? But again, the alpha and the beta part, not a big deal. Use a piece of paper, use a piece of metal foil, that will stop it. But the gamma rays, the high energy nature of the gamma rays, and the fact that they're not composed of matter, just think about when you have a shirt on. Your skin still gets hot from the sun, even if you have a shirt on. Well, because that energy can go through your shirt. Well, gamma rays are like that, but they're just way, way, way worse. Okay, it's like a million sunburns all at once. Okay, and then your skin turns red, you start to bleed. Again, gamma radiation is not something that you want to be near at any point in your life. Okay, so here's an example of this. You've got a uranium atom that has 92 protons. When that happens, again, we can see that an alpha particle, that's the alpha particle there, being released. As well, it does turn into another element with 2 less protons, which is thallium. And then again, there's the gamma radiation being produced from that. Okay, so 3 different types of radiation: gamma, beta, and alpha. Again, the first 2 are made of matter. The third one is just very, very high energy waves. Again, here's a good summary of all of them here in this chart. Again, most of the stuff is not that important in terms of what do I need to memorize. This is certainly something that I would know what it is, probably their symbols, probably what you need to. I mean, look at gamma radiation. It's not completely blocked even by lead or by concrete. So, and it's just like a sunburn too. You don't even realize you're getting hit by it. Okay, you're standing there and you're like, ooh, look at that cool fire at that nuclear reactor, while you're getting blasted, just like the sun. You're getting blasted by the sun, and then 3 hours later, you're like, oh, I have a sunburn. Well, again, this is like a million sunburns all at once. Okay, and that is just a brief introduction to nuclear chemistry and nuclear reactions.